Let's look at the following RC circuit problem. It has a 12-volt battery attached to two resistors in series, which is then attached to a capacitor. And initially the switch is in position A, which means that the capacitor is getting charged. We're going to assume that the capacitor is initially completely empty. So the first question is, how long does it take to get 50% charged? Now, after a very long time, assuming the capacitor is completely charged, the switch is then thrown to position B. And that's when the discharge happens. The question about the discharge circuit is, when is the voltage across the resistor R3 equal to the voltage across the capacitor? To solve each part, we need to first find the relevant time constants. So in position A, R1 and R2 are in series. So the effective time constant is going to be given by the capacitance times the effective resistance in series, R1 in series with R2. And since Ri is equal to I kilo ohms, R1 is 1 kilo ohm and R2 is 2 kilo ohms, and resistors in series simply add. So that's going to be 3 kilo ohms times 20 mu f. So I'm going to get 60 kilo and micro interact to produce a milliseconds. That's the time constant for the circuit in position A. The capacitor's charge at any given time is given by the eventual charge Q infinity times 1 minus e to the minus t upon tau A. Let's see what this gives us. Q of t is supposed to be Q infinity over 2, because that's what it means to be 50% charged. That automatically tells us, because for Q infinity over 2 I need 1 minus half, because 1 minus half is half. So this tells me that e to the minus t over tau is half, which can be written as 2 to the power minus 1. Now if I take the natural log of both sides, I'm going to get negative t over tau, natural log of e, which is 1, is equal to negative 1 natural log of 2. I don't have a calculator, so I'll just have to leave the natural logs as it is. So the natural log of e is just 1. So the time required is just tau A, which is 60 milliseconds, times natural log of 2, which I recall is something like 0.693. So I'll just say it's 0.7. And so that's going to be about 42 milliseconds. So that's the answer to the first question. The capacitor gets charged in about 42 milliseconds to 50% of its value. Now it's getting charged and it's getting charged, so a long time elapses, and then the switch is thrown to position B. You now have a discharge circuit. So the equations, first of all, let's find the time constant for position B. That's going to have a capacitor with two resistors in parallel, because these two are in parallel. They have the same node there and the same node here. So the same voltage occurs across both R4 and R3. Capacitors in parallel add harmonically. So I'm going to have 20 microfarads times R3 R4 divided by R3 plus R4. So that's giving me 20 mu f times 3 kilo ohms times 4 kilo ohms divided by 3 plus 4, or 7 kilo ohms. As before, kilo and micro interact to produce milli. This is 12 divided by 7 times 20. So that's 240 over 7 milliseconds. I'll just leave it like that. Now, once you have the time constant, you can then maybe you don't even need the time constant. I just found it because it's a fun thing to find. Observe that the time constant is different now, 60 milliseconds, and now it's 240 over 7, which is much smaller than 60, I'm guessing, because 7 times 40 is 280, so it's less than even, but 7 times 3 is 21, so it's between 3 and 4, so I'm guessing it's going to be something like 35-ish milliseconds. The number is not important, it's just less than that. Okay, now let's figure out when the voltages are going to be equal. The voltage across R3, incidentally, is the same as the voltage across the entire resistance combo, because the voltage across R3 and R4 are identical. So what we need to do is find the voltage across the capacitor and set it equal to the voltage across any one of the resistors. The voltage across a capacitor is found by taking the, remember the equation that governs capacitance. Capacitance is charge over voltage, therefore voltage equals charge divided by capacitance. Now the charge as a function of time for a discharge circuit must be used, and that should be equal to the current as a function of time for the discharge circuit times the resistance by Ohm's law. Alright, let's figure this. Q of t is Q naught e to the minus t over tau b. I of t is the initial current I naught times e to the minus t over tau b. Times R3. So, not surprisingly, we attain we have the obvious result that the voltage across the capacitor is always going to be equal to the voltage across the resistors, because that is one of the conditions of being in a circuit like that. So let me just explain that. So I have a capacitor which is basically sitting across a resistor combination, which is R3 in parallel with R4, and the voltage across the capacitor is always going to be equal to the voltage across the resistor combo. So this is basically telling us, oh, it's always going to be true. Let's actually use this to find the initial current in the circuit. So let me modify my problem a little bit. Let me do a third part. What's the current after two time constants? And also what's voltage across R3 after two time constants? So let's make the problem a little bit more interesting. So part 3, so this is always valid for all times. For part 3, we have to find the initial current I naught. You can either use this equation to find I naught, or you can simply go back to using the Q infinity. The Q infinity is going to be the initial charge of the new process. So the Q infinity there was equal to E divided by the E times C, excuse me, that's going to be Q infinity. That's when the current completely stops flowing and the voltage, the charge is just given by the voltage times the capacitance. So that's going to be 12 volts times 20 mu f, or 240 microcoulombs. That's Q infinity, and that becomes Q naught for the new story for switch B. Okay, now that we have Q naught, we can in fact find the initial current using this logic. The initial current I naught is going to be the voltage across the capacitor divided by the effective resistance, because that will certainly give us the initial current that the capacitor puts out. So the capacitor should be thought of as a battery now, and it's putting out some current, and that's going to be the voltage across the capacitor divided by the effective resistance. That's in fact going to be the current at any given time, but initially the voltage across the capacitor is a full voltage. So it's going to be Q naught or Q infinity over C times RF. So Q naught over C, or Q infinity over C, is just E, or 12 volts again, over the effective resistance, which we found here to be 12 over 7. So that's going to be 7 milliamperes. After two time constants, the current after two time constants is going to become equal to e to the minus 2 times I naught, because that is the definition of the current as a function of time. I as a function of time is equal to I naught e to the minus t over tau b, and after two time constants, which means you're putting t equals 2 tau b, I'm going to get negative 2 tau b over tau b, which is negative 2. So I just get e to the negative 2, which is something like 37% of 37%. It's a small quantity. I'm not going to bother with the numerics again. So the answer is going to be 7 milliamperes times e to the minus 2. Whatever that is in your calculator, that's the answer. The last part is what's the voltage across the resistor R3 after that time, after the two time constants. You can do this two ways. You can either find the current through the resistor and its value. We already know the total current is 7 milliamperes times e to the minus 2. So what we can do is use the total current. Now if you have R3 and R4, the current flowing through are the same. Okay, let's put it this way. The current is going to divide up into two currents. R3 is going to get a little bit more because it has less resistance than R4. But no matter what happens, the voltage across them is going to be the same. And it's going to be the same as the voltage across a capacitor. So we might as well find the voltage across a capacitor rather than mess around with the currents. The voltage across a capacitor after two time constants, or Vc as a function of t, is just Q as a function of t divided by C. Well, Q as a function of t is Q naught e to the minus t over tau b divided by C. Q naught itself is Q infinity, which is E times C. So this whole thing is just E times e to the minus t over tau b. Therefore, the voltage across the capacitor at two time constants, which is going to be the same as the voltage across either of the resistors at two time constants, because they're always going to be the same by the same logic as part 2, well, that's just going to be this. So it's E times e to the minus 2 tau b over tau b. So that's going to be 12 volts times e to the minus 2, again whatever that is in your calculator. So this way we have solved the entire problem.